Oh, yes.
Oh, no,
So what's that?
today's Yeah, no, just like everyone. Yeah, you can probably do it in a really low tech way.
Somebody can find a marker.
Yeah, that's.
I don't know how much.
Yeah.
Okay, perfect. Thanks.
What?
I want to actually get a class. Anything left in it. So linear regression, right? That's where we were. Let's do a quick recap and then rethink those derivations there. We have X, the data matrix. X1, 1, D. We have Y, the labels. Y1, Yn. And we have a vector of coefficients, W, which is 1, 2, up to B. We have a H, the regressor. On any data point X, which X is really X1, X2, XD, right? It's a vector. It's the W times X. So let's see if the dimensions align, right? This X is of size 1 times D. And W is size 1 times D. It doesn't work, right? You can't say WX. Multiplication won't be correct. I have to make sure. We won't penalize for this kind of thing if you write something like this, but in general you have to make sure dimensions align. So how do I do this? One of them has to be transposed, which is which one? If I transpose W, what's the dimension I get on W? D1 times 1 by D. Is that good? No, that's D times D. I don't want to do that. So what I would like to do is 1 times D, then times D times 1, right? To get a value. So to do that, I would have to do what? Like that? Okay. So in general, again, in this class, we've been formal about this. If you write W times X, I'll understand that you will mean the dot product and not some other weird thing. But when you write formally math, you have to be correct about it. So then this is the regression function, and then we have the loss or the error, which is associated with the coefficient, which is h of x minus y squared. So that's for every data point, say I. And that has to be the sum over all data points, 1 to n. I take the difference between the regression value and the y value, and I square it. We said that if the regressor is a line like this is where the data point is. This is where the h of x is, right, on the line. And this is maybe where the y is. The square that the distance that I'm squaring is this chunk here. The difference between h of x and y. So I'm going to say that this whole thing is exactly this distance squared. And that's for one x. I may have another x, another x, another x. I square those things and sum them all. Good. And then we say, okay, well, this I can write as, we said we're going to put a 1/2 in front of it for mathematical purposes. The constant won't change how the function behaves. So we'll add this 1/2 to get the 1/2. I have here it's x w minus y transpose x w minus y. Presumably, if you do those calculations, you get exactly this summation here. Something to verify. And then what we said is we want to minimize the loss. As a function of who? W. Because x and y are given to me. This is the train set, right? I have no choice on x and y. So as a function of w, I'll take the differential with respect to w. I'm going to say differentiate delta j of w at delta w. That's a vector. Right? So in principle, that's what we did last time. We kind of washed it out. We say, well, it's a vector, but we're going to apply the same differential that we know from the scalars, right? That's what we said. And we actually call it delta w of j, like that. And we said, well, if we compute that differential, right, this is last time, we got x transpose x w minus x transpose y. And we said minimize this means differential should be 0. That's how we minimize a function. And then we said if we want to set this to 0, then by some manipulation here, multiply with the inverse of the coefficient here, we would get w equals x transpose x inverse times x transpose y. And this is called the normal equation or equations. It's also an exact solution. Exact global. We have some math that says this is the absolute best W that you could get to minimize this loss. It's not a trial and error thing. It's like you saw 2x plus 5 equals 7. You get exact out of that equation. Right? So the reason we know it's a global exact minimum is that we know this function 1/2 sum for all data points h of x. that is sum over all dimensions, WDXID, right, minus YI. This H of X here is the dot product between the W coefficients and the components of X. So the dot product is here, the dot product is sum of products over all components, right? Minus YI, the square is the square, and summed up over all the data. This is a convex function in any WD. That was a little argument we had last time, right? Somebody, I mean, we saw that way for one, somebody was pointing out for one, if I only have one data point, I look at that, that's convex in W. But how about the summation over a few data points? They have 1,000 or 4,000 or 100,000. It's still a convex function. Did we figure that out?
So first, you can just swap the order of the sums, but also in the convex optimization notes, there's a proof that shows that the sum of the non-negative weights of a convex function is itself a convex function. Here, the weights are all non-negative.
What weights? W?
Sorry, the weights on the sums. Like if that inner part is a convex function, you think this is a weighted sum of convex functions with a weight on each is 1.
Okay. So he's saying if I have a bunch of convex functions, that's what you're saying, and I add them up, we say with weights 1, let's not worry about weights. If you say if you add a bunch of convex functions together, you get the convex function. Is that true? I don't know. What he's saying is F convex, F and G, convex functions. Then F plus G is convex. Right? What you're saying? I mean, maybe there's a weighted version of this, but the one we say we need is just one. So if you're saying if for every data point is convex, well, add them up over all the data points, that's convex too. Is it true? Or not?
Are convex functions a subspace of something?
I don't know. What? It's a subspace?
No, just like, are they a subspace of some other?
Set of functions.
Yeah.
I mean, that's what we're trying to get in here.
Because if they are, you could just prove like closure and the scalar to say yes.
Just to be clear, my inclination here is not to teach a course in mathematics. I don't want to do that. But you guys need a way to handle basic stuff, like convexity. You don't have to know the whole theory of convex functions. But in this notion here, this is a very simple quadratic function. How do you handle that? Let's get down to basics for the people who know a lot of math. Can we cool off for a second and just get to reality? How do we handle a simple convex function? What is it? What makes a function convex, first of all? When a function is convex. So we put last time a plot on the board that says had look like that, right? That's convex. And looks like that means we know the minimum is a global minimum. It's right here. There's no other minimum. There's no other point where the differential is 0. Fine. But how do we define this mathematically?
Quadratic equation.
A quadratic equation has the shape if the first coefficient is positive. But not all shapes like this are necessarily quadratic. Right? So we need a general convex function. Yes.
Like if we take 2 points and join them.
So say x1 and x2,
Yeah.
maybe?
So all the function points lie below that.
Join them, what does it mean to join them?
A straight line.
Like that?
Yeah.
Okay.
So all the points should lie below that line.
All points.
Between x1 and x2.
Like I think what you mean is if I pick another point here, x, the value of the function in this x,
Yes.
it's below this line. Right? So what he's saying, if you take this x and you say, okay, what is in here? That's f of x, right? And what's in here? X intersecting with this line. I'd say it's enough to do this for the middle. It's true that it has to be correct for all the points x, but as a definition, of convexity, we're gonna pick the middle point, which is x1 plus x2 divided by 2. And that's enough. If that works for any x1 and x2 in the middle, you can prove it's actually working for every single point around here. So how do we express this property that the value of the function in this point is smaller than whenever this intersects the line? So we're gonna say f of x is smaller than, what is the height in here? Because this is in the middle, isn't this in the middle of those two? Median, so which ones are those two? This is f of x1, right? This is f of x2. So this is f of the middle, x1 plus x2 divided by 2 has to be smaller than f of x1 plus f of x2 divided by 2. So what this is saying, if you apply the function f in the middle, in M, the value you get, it's smaller than if you apply the function here and here. You get f of x1, f of x2, and you take that average. That average is here. So this one here, let me write it down this way. It's f of x1 plus x2 by 2. And this point here is who? F of x1 plus f of x2 divided by 2. The f applied to the average argument, it's smaller than the average of f values. So the opposite concavity would be exactly the opposite. If I want the function to be backwards, I'll have the exact. That's for the middle. Now let's write it for every point M, not just the middle. So I'm going to say M is between x2 and x1, but not the middle necessarily. It's any point in there. I can express M as a combination of x1 and x2. I'm going to say it's some weight on x1 plus some weight where alpha is between 0 and 1. Is that true? If I do these linear combinations with alpha 0, what do I get? x2. And with alpha 1, I get x1. So in alpha travels this interval, this point M travels exactly from x2 to x1, right? So if I say I want all the points in this interval, that means all the combinations of some weight times x1 plus some weight times x2, where the weight is between 0 and 1, and the two weights have to add up to 1. Hands up, who's with me? Hands up who's seen this particular way of defining an interval. To go from here to here, it's a combination of the two endpoints with various weights. If I set the weights 100% on one, I'm in that point. If I set the weight 100% on this one, I'm in that point. And in between, I'm going through the whole interval. In particular, this is corresponding to what weights? This middle point. 0.5 will give exactly the middle. But with different alphas, I can get different points. This is 0.5, but I can get this point, this point, this point, this point, this point, this point, so on and so forth. I get all of them. How do I write this inequality now? It's not for the middle, it's for that point. I want to say f of alpha x1 plus 1 minus alpha x2, right? That's my point. It's a combination, could be 50-50, but could be 20-80 or some other combination. Has to be smaller than what? What's the right side counts? And at the denominator? 1, which is actually alpha plus 1 minus alpha. Sometimes you see this written with two coefficients, alpha and beta. If you have it that way, you might see alpha and beta here. It's the same principle. F applied to some combination, it's smaller than the combination applied to the F values. That's the definition of convexity. Okay? Now, we would like to prove that this function is convex. Naively, we could use the definition and try to prove that according to the definition, this is a function in many variables, right? Because that one only has an argument x. This one has as an argument w1, w2, w3, so on up to wd. And we're saying it's convex in any one of them. Meaning if you keep all of them except one fixed and just vary w3, in that argument w3, when the other w's are completely nailed down, they can move. In that argument, that's a convex function. If I keep w5 variable and all the other w's fixed, then in w5 I get the convex function. See, this is a function of d variables. Now, I could try to apply the definition, but that's going to be very messy, right? So I don't want to do that. I need a theorem that I'm going to not prove here because it's from high school calculus. A function is convex. A function that's differential. It's convex if and only if
It's derivative 0 in one place.
I told you. A function is convex if and only if a differentiable function, like a nice function.
Positive.
Who's positive?
So the first non-differential.
Close. Nobody knows
The
this.
second differential.
Second differential. Second differential. So sometimes we call that f second, or sometimes delta f, delta f is positive. That's the same as saying that f prime, which is delta f, the second differential is the differential of the differential, right? So to say that the second differential is positive, it means the function that got differentiated, which is the first differential, has to be, when is the differential positive? When the function that I just differentiated is increasing. So that's to say this function has to be monotonic. Increasing. So the first differential is increasing. That's the same as saying the second differential is positive. Is the first differential increasing? This looks like a negative differential. This tangent. Differential is the tangent, right? Is this going negative? If I advance a little bit, it's less negative. If I advance more, it's less negative. That means the differential is increasing, right? What happens if I get to here? Differential becomes 0. And then when I move a little bit, differential becomes positive, and then more positive, and then more positive. You can see on this curve, if it looks like round and nice down like that, that the first differential, which is the tangent, slowly it's increasing. And it's never decreasing, right? If I see, you know, here's the function, and it kind of starts with a very, very negative differential, and then it's more positive and more positive and more positive, and it gets to 0, and then it's increasing. How would I get the differential in this point? It looks like that, right? What would it take for this function now to start decreasing its differential? What the function needs to do so the differential starts decreasing? The tangent has to go back down, which means the function has to go this way, right? And you can see how it loses convexity. It was convex up to here, and in here the curvature starts being different. Now what about the differential that's being constant? It's not increasing, it's not decreasing, remains the same. What do the function need to do? Be a straight line.
So there are functions that have only one minimum that are not convex, right? Convexity isn't the only thing that guarantees. You can have a function with no local minima that are not with local minima. That are
So if you have a
non-convex.
minimum, intuitively speaking, here's a minimum. And if you want to have another local minimum, say it's in here somewhere.
Right, to have a local minimum, it must be non-convex, but you can be non-convex and still have only one local minimum.
I think so. I have to think about that. But certainly if you have two local minimums, I think that's an argument against convexity. Okay? I use a little bit of time to do a recap of calculus. That's a good thing. Not necessarily helping with the homework. This is a theorem that we don't require, but if you are math inclined, you should. It's a long weekend, right? Martin Luther King weekend. Take a look at it and say, hey, who remembers that from high school, right? Is that true that functions that satisfy this and that differentiable, they must satisfy this? I give you an explanation with my hand over that's not mathematical, right? Can you go home and write down a mathematical proof for why is it that convex function have a positive differential? I won't prove that, but if somebody tries and doesn't know how to do it, come to office hours and figure it out. I mean, the proof is very public everywhere you look. Now that, I think, can help us here. Not the definition, but this theorem. We want to prove that this is convex, right? So what's the differential of this? The second differential. So that is J second, which is double J with respect to one of the variables. Not the whole vector W. Pick one W, say WD, one of them. W3, 5. Each W is associated with a column in the data, right? Each column has its own W here. And we said we have an extra W0 that multiplies with 1 to get ourselves a bias. Well, so when I differentiate this J with respect to some particular W, this is a normal function. It's not a vector function. It's not a matrix, right? All the other W's are fixed except this one. Let's pick W1 to be more clear. In W1, what kind of function is this? If I say everything is constant here, x's are constant, y's are constant, the other w's are constants, w2, 3, 4, 5, they're all constants. The only variable is w1. What kind of function is this in w1? This is a quadratic function, right? This in w1 as a function of w1 alone, this is some a times w1 squared, right? Plus b w1 plus c, where a is whatever summation comes up, right? Can everybody see that? That the coefficient of w1 squared is some sum of x's and so on and so forth, and then there's some x and y's, and then some free term, right? So the second differential of this function with respect to w1, what is it? This quadratic function, if I, it's 2a, right? Okay, differentiated once, you get 2aw plus b, and differentiate the second time, you just get 2a. So what's that coefficient of w1 then? Who's a? Who's w1 multiplying with?
Sorry, what?
X, 1, 1. Is it squared?
Yes. Yes.
So the coefficient, I'm only looking for A, right? I don't care about B and C because when I second differentiate, coefficients B and C won't matter.
Yeah.
I'm only looking for the coefficient that W1 is going to have in this summation, W1 squared. So the square one, is it going to multiply with X1, 1 squared? Square. Plus, there's a massive plus in here. There's a summation, right, over all data points. So what's the next? X 2, 1 squared plus x and 1 squared. Now W 1 will only multiply with the first component. First, right? X1, 2 will multiply with a different W, so that won't matter. Hands up. Who's with me so far? Okay, I missed the 1/2, right? 1/2 coming from here. So my point is, when I differentiate twice this function with respect to W1, I'm going to get 2a, right? So that's going to be the sum for I equal 1 to n of x I1 squared. Because it's this times 2. And this is a positive quantity, right? Because it's a sum of squares. That's a positive quantity. My theorem will say you got a positive second differential, you got a convex function. Right? So now, are we sure it's a convex function? Yeah. Good. But you still have to prove this theorem to be sure, like 100% sure. Okay. Good. So that being said, we said there's some problems with this. Even though this is an exact global minimum solution, it's quite impractical. Size of the matrices might be an issue. How big is this x? This x. So what's the dimensionality here? Just a quick recap. Y is, this has to be, this whole result has to come out as 1 times d, right?
This would be d by 1.
What?
In this state, it is d by 1.
D by 1. D by 1. So how is this going to work? This has to be a d by d matrix. This has to be a
Y is
d by n. And this has to be a n by 1, right?
Yeah.
And x transpose x, it's going to become d by d because it's n d transpose as dn times nd is d by d, right? By the way, this x transpose x, it's an enormous important matrix in statistics, in data science, machine learning, so on and so forth. This is a covariance matrix right here, right? Or empirical covariance, so to speak. And mathematically, this has a very important properties. It's a symmetric positive matrix. Symmetric as in across the diagonal. If I transpose this matrix, I get the same matrix, right? The transpose xtx, everything transpose. What is it? xt, xtd, right? That's xtx. So that's a symmetry matrix. And mathematically, these have positive eigenvalues, very nice properties. So every time you get your hands on xtx, it's a nice situation to be in. Good. So one issue might be the data sizes. How big are those matrices and what does it take to multiply them? Another bigger issue is the inverse. The inverse requires the determinant of a matrix to be non-zero. But even if it's non-zero, yet close to 0, the inverse becomes an unstable operation if the matrix is big. So now you may say d by d is not that big, as in typically in data sets that you've seen, n is bigger than d, right? N is 4,000 data points and d is 50 features. But there are data points out there that have 100,000 features, typically for text. Or for images, if you use every pixel as a feature, if you have a picture from your phone that's 3,000 by 3,000, that's 9 million pixels right there. So you could have a lot of these, and then this becomes a complicated operation, in particular the inverse. Even though computers now can handle the size, even 9 million, the inverse is a problematic operation. So if you do this, which is not what you do in practice, but you do it for the homework, you want to look for a pseudo-inverse operation here, something that's not exact, but decent, doesn't go too high or too low. All right, so we have that. Now, we have a derivation last time that was a little, like, as I said, I applied the mechanics from scalar derivation, which everybody knows, to vector derivation. And I kind of said, you know, maybe the mechanics work. Now, I want to kind of redo that for a few minutes, but the right way. So to do this derivation, to get this last time from the differential to this equation, I need to introduce something in order to skip over the, let's assume the gradient for vectors works in the same way as for scalars. So here's what we need to do. We're going to need to introduce an operator here called trace of matrix. So you're going to call it trace of A the sum of diagonal elements. So how much is the trace of 1, 5, 0, minus 3? It's 1 plus minus 3, negative. The other thing that we need to introduce is how exactly that differential works. So I'm going to have a function of a matrix. For example, the trace. But it doesn't have to be the trace. It could be, for example, the trace. Here's another example. F of a matrix A, that's 2 by 2, is, I have here 3 half A11 plus 5 A12 squared plus A21 times A22. So I have a function that takes a matrix, produces a real number, and produces a real number by doing something with the elements of the matrix. So the trace would be trace of A, if it's A is 2, 2 would be A11 plus A22, right? That would be this function, trace. And here's another function. The differential definition of this function is a matrix that is the differential of F with respect to every single element. So the function produces a real number, but when I differentiate it with respect to a matrix, I get n by n functions in there because I differentiate that function with respect to A11, A12, A1n, so on and so forth. So what's about the trace? If I take the trace differential, what would that be? The differential with respect to A11 is 1. How about this one? 1. This is 1. The differential with respect to every other element is 0, right? Because the other elements don't contribute to the trace. So I have some properties here about the trace, about differentials. One is saying the trace of a product is the trace of the other product. I think you know that the product is not a commutative operation. So generally speaking, for matrices, A times B is not the same as B times A. But the trace is the same. You can verify this manually. You can compute the summation of the elements on the diagonal here, and the summation of elements on diagonal here will be the same. How about trace of A transpose? It's trace of A. Is that true? Yeah, because when I transpose a matrix, the diagonal remains the same. Trace of A plus B is trace of A plus trace of B. That's easy to verify. What are the elements on diagonal A plus B? Every element in position II is the AII plus BII, so the sums work out. And finally, the trace of a scalar times a matrix, I can take that scalar out, right? Because the diagonal will have all the elements multiply with that value as, say, 17. That's 17 times the sum of the. How about differential? The differential with respect to a matrix of trace of AB is B transpose. That's something that you guys have to go home and check it out manually. There's no, just, we apply this thing, right? The differential of A with respect to a function, it's a matrix, right? So that's a matrix, that's a matrix. How do we verify that two matrices are the same? Each element. So we take, what's the differential of trace AB? That will mean the differential of trace of AB with respect to A11 should be B11. How about the differential of the trace of AB with respect to A17? So that has to be verified at A times B. We know how that works, right? It's every element has a bunch of dot product in there. Trace is the sum of the main diagonal. You look at that sum, take the differential, we're going to get this element. So that's one property. How about differential with respect to A transpose of a function A of A? It's the differential of A f of A transpose. And I have two more. Differential of trace AB A transpose C AB plus C transpose transpose. And finally, the last one I need, differential of trace we are not going to require this, that you know those formulas, or even how the differential of a matrix work. So if you say, okay, I don't want to deal with this math, that's fine. Your grade not going to depend on this math. But the exercise of going through these calculations and check them out, that's quite useful for data science in general, because you have to get some fluency into working with matrices. And in my experience, master students don't have that fluency. They're more inclined towards programming and not so much into matrix and calculus. So if you have the time, you can check those out, but they're not required for the class. Now that we have this, let's redo the derivation from last time. So we have this formula here. What is it? Here. So we're going to differentiate with respect to W, J of W. And we're going to get differential with respect to W 1/2 XW minus Y transpose W minus Y. The first step is like before, it's 1/2 differential with respect to W of, we can open those parentheses, W transpose X transpose X W. That's the same like before. W transpose X transpose Y. Y transpose X W plus Y transpose Y. And now because this is 1 by 1, right, this is a value, I'm going to call trace of it, because trace of a 1 by 1 matrix is that element. Right? So now I've got myself into this framework where I apply the differential with respect to a matrix to a real function, the trace. So let's see what happens. I'm going to have here trace of W transpose X transpose X W. Minus 2 trace of Y transpose X. So how did that work? First of all, I got rid of this. Y transpose Y. Why is that? There's no W in there, so the differential with respect to W on that will be 0. And when I get two of these? What's the relationship between those two matrices?
One's transpose, the other.
And what we know about trace?
It's the same.
It's the same, right? So this is the transpose of that. So they all, in terms of trace, they the same thing. 2 times trace of that. So now I got 1/2 in here. I'm going to get X transpose XW plus X transpose XW again. And in here, I'm going to get minus 2X transpose Y. That's everything in 1/2, I think. Everything is 1/2. So I think this one is easy. Which formula I need to apply here to get this? It's the differential of a trace that's some matrix times W. So where is that formula? Differential of a trace that's a matrix times the one that I'm taking the differential with respect to. I think is this formula right here. Is the differential with respect to a matrix of the trace. Like I have a trace here, I have a matrix times W. So the result of that is the other matrix, not the W transpose, like in here. Differential with respect to A, it's A times something. Could be B transpose times A transpose because that will be the same thing. The differential is B transpose. So the differential will be the transpose of this other matrix that multiplies with W. Ends up to 0. I mean, I can apply this formula and get that answer. How about in here? In here, I think I have to apply one of these formulas. I'm going to let you figure this out, but I'm going to tell you who's who. To apply these formulas, I need A transpose from the formula to be W, B and B transpose to be X transpose X, and C in this formula to be the identity matrix. Now let's look at this formula. If I replace A transpose to W, B with this and C with I, who is A, B, A transpose C? Who's A? W transpose. Who's B? X transpose times X is right here. And who is A transpose? W. And C is identity. So then the formula says you're going to get B transpose. Who's B transpose? B transpose is X dx. So that's right here. Times A transpose. Who's A transpose? W plus B X transpose X times A transpose W times C. So that's that. And that's exactly the formula we need, right? At this point is done. X transpose X W minus X transpose Y. From here on, it goes the same, like now. This differentiation, it's mathematical. It does not apply that mechanic from scalar to vectors hoping it works. It does it the right way. But we still haven't proven this formula. We have the introduction, what the function is, what the trace is. I think you guys believe me on those equations here. I think you understood how the differential works. You differentiate the function with respect to every single element of the matrix and you get a matrix of functions. We have to verify this and this and this and that, which I'm not going to do in class, to be complete. If we really, I mean, you can believe me that this works, or we can do the verification. The verification is manual, meaning with pencil and paper. What is the differential, for every element? To get two matrices being the same, or these two matrices being the same, you have to verify that every element here is like the same like every element here. Your homework contains an extra credit problem, which is one of those two. So it's just grinding numbers. This is not hard. It has to be done on pencil. Okay. But this way, at least, we have a mathematical derivation, not a hoping that's going to work. Good. So now, I want to talk about some regression properties. And in the meantime, we're going to introduce more concepts. So what is so good about regression? The loss is convex. So that implies a global mean. We already talked about this. What's also good? The classifier is a hyperplane that is aligned in 2D. A hyperplane means it splits the space in half. So I have some minuses here, some pluses on this side. Intuitively, a separation like this, it's a very simple separation, right? Like I'm trying to separate the people who have diabetes versus the people who don't have diabetes. The simple possible separation you can imagine in the space of the data, which is not up to the regression algorithm. The space is whatever the space is, whatever the features are provided. The simplest possible separation is to cut a straight line of hyperplane there, right? So that means simple. Simple is good. There's a famous philosopher, Occam's razor, that said, maybe Einstein rephrased that a little bit. Says, if you can explain something simple, prefer always the simple explanation. So if you can separate things with a simple algorithm classification of the world, that's the one you should use, not a very complicated one that doesn't explain. Okay. What's another thing? It's very fast. You should see that for your homework one, for example, solving this normal equation, even though you have to pay attention to the inverse, you have to find the right library to call in this homework, or in all homeworks, you're not required to implement the math. So how to invert a matrix? You just call a function for that. So we say write your code from scratch. We don't mean that you have to implement matrices and inverse. You have to write the algorithm on your own, but the actual calculation you can have MATLAB or Python doing for you. That's a very fast calculation. So if you compare your regression time with your tree time, right, the decision tree or the regression tree, regression will be much faster if you call the right library and if you don't get stuck with the inverse. So it could be very fast. It can be very accurate with many features. Many, I should say, typically sparse features. That's a property I talked about at office hours with some of you, where you have to look at the regression formula. H of x is W1x1 plus W2x2 plus W, say, k xk, right? Plus wk plus 1, xk plus 1, up to k plus m, xk plus m, that's another chunk, plus x plus k plus m plus 1. You can look at, these are all the features that sparse features means features that only appear in very few documents. It's very typical for text. Every meaningful word will only appear in very few documents. Something that appears in all the documents is probably not a meaningful feature. So if this appears only in a bunch of documents, say I have 500,000 documents, but the word China only appears in 25 of them. What happens is the other documents don't have the word China in them. How does that translate into a feature value? If they don't have the word China, the X China for those documents will be 0. If it's 0, it's W here. If it's 0, it doesn't matter for the loss what regression coefficients are for that feature, right? In other words, the penalty for assigning a certain W for the word China only gets, the penalty in the loss gets computed from the documents that contain the word China. The other documents have a 0, so when I do the multiplication X times W, doesn't matter what W I have, I get a 0. If that's the case, then every one of these chunks in the regression summation acts independently. This is a line that fits the document that contains the word China. This is a different line that fits the documents that contain some other word. This is a different line. So that way, it's not a simple classifier anymore. Of course, that makes sense in few dimensions. If you look at it overall in a space of many, many dimensions, it's still a hyperplane, but it's a very complicated hyperplane. So that will take some time. It's not a simple thing to swallow, what I just said here. It's just the more features we have and the more sparse they are, regression gets increased complexity. Same thing happens with the tree when we develop the tree down, right? When we push the tree down and we keep splitting, we increase the complexity of the classifiers. Why is that? Each leaf of the tree, the more we push it down, each leaf acts on the size of the data set that becomes smaller and smaller and smaller. That's very typical. Complex classifiers are the ones that can do different things for different chunks of the data. That adds complexity. So how do we add complexity in here? Why is this becoming complex? In the span-based data set, it can be complex because it's a line in 50-dimensional space. And the features, those 50 features that you have, are not sparse at all. If you look at the values they have, a sparse feature will have 0 most of the time and non-zero sometimes. That's not the case with these span features. They are some real values most of the time. Same thing with the houses. The houses, if you look at a particular feature, I don't think you're going to see mostly 0. So for those cases, regression is kind of limited in complexity, right? The most it can do is have a line. It can pick the hyperplane or the line, but it's the best line within that space. Once we add sparse features, we allow regression to concentrate differently on different regions of the space. That immediately adds complexity. So there's no surprise that on text classification, you're going to see a data set in a week or so, 20 newsgroup, has, say, 18,000 documents and 25,000 features. It's very different than span-based, which has 40,000 documents and 50 features, right? So that's 80 times more documents than features. The other one that you're going to see next will have more features than documents. They gotta be sparse, right? You can't have all these features, right? So in that sense, we can have regression being a complex classifier. So this simplicity here, it's a little tricky business. You can say it's simple in the sense that it's a line. How much more simple something can be than a line, right? Well, if you think of it in a high dimensional space, that line is with sparsity, it actually very many classifiers on different regions of the space. So it could act in that sense like a decision. I mean, it doesn't act equivalent to decision tree in terms of classification, but it has increased complexity. A lot of machine learning on non-trivial data, not the data that you can just run and get the result, will come down to addressing the complexity of the classifier. Complexity is also a function of data. A classifier can overfit with so many dimensions only if it doesn't have enough data. even for 20 news groups, if I have 25,000 features, instead of 18,000 documents, 18 billion documents, then it cannot overfit anymore. The more data, it's much larger than the feature space. A regression line cannot overfit. To overfit, I need to have sparse features, many columns, and not that many data points. All right, what's bad about it?
Simplified. It assumes a linearity.
Linearity assumption. May not hold. Here's a very simple example, right? What happens if I have a circle and everything inside the circle is a plus? It's a two-dimensional data, x1 and x2, and everything outside the circle is a minus. Can you draw a line here to separate pluses from minuses? No. There's no line that fits. Which kind of example is this one? Is this one with many features where regression can have many lines in different parts of the space? How many features I have here? Two. This is the case where it's simple, and because it's simple, it cannot succeed. No simple classifier can succeed in here. Can a decision tree succeed in this data?
Yes.
What a decision tree does in a two-dimensional space, all the splits represent geometrically what? Cuts that are either vertical or horizontal. Because every time you pick a feature and a threshold, if you pick this feature and threshold, you cut the data set this way, right? So decision tree might succeed, but it's gonna take a while, right, to succeed. Like say a cut can come here, then another cut might come here, then another cut might come here, and one cut that's here, it still does something. Can I cut this way? Can the decision tree cut it this way? No. So then in this region here might be something like, okay, do something like this, and then do something like that, and so on and so forth. So it might take a few cuts to get everything right, but it can succeed with a deep enough tree. A regression will never succeed. There's no line that will separate the pluses from minuses, no matter how hard they try. Okay? What else?
When there are too many features, won't it overfit?
Yes. This case here.
Yeah.
Accurate on training. I mean, I can get 0% training error with many features, and as a consequence of that, will also overfit. This is a direct consequence of this kind of case where I have many features and I can get whatever I want effectively. I can overfit any data, not big enough. Like 20 news groups has more minimal features than data points. I can overfit it. That doesn't mean I'm going to get a good prediction on the test set. So yes, overfit with many sparse features. What else? That's bad.
Outliers cannot be detected.
Outliers. Let's think about that. What's an outlier here?
A minus.
A plus which is
A minus here would be kind of an outlier. A plus here would be an outlier, right? So, who has a better chance of do this right? But by right, I mean truly right. As in get not the training error 0. That's not what we want, right? We don't want to get everything right on training. We want a generalizable ability, whatever we learn, to be able to work on the next spam email or the next document or the next patient. So in this case, if I use a decision tree and I try very hard to get all the points right on training set, I'm going to learn that in this region of the space, that's a plus zone, right? If I push the tree down enough, if I make it long enough, eventually it's going to say, well, for some reason I get the plus over there. Maybe that's not, normal, but that's what I learned. A regression cannot compensate for an outlier. So in this situation, regression doesn't work at all because the data is constructed to be antilinear. But suppose I do have a regression data set. So I have a line that is the line, there's a bunch of minuses on this side and a bunch of pluses this side. There's some minuses that are in the plus zone and some pluses that are in the minus zone, but the errors that are not outliers are the one close to the line. That's where the patient, kind of, it's about to have diabetes, doesn't have it yet, it's on the other line, may get it tomorrow, It's the gray area of we not sure, right? Even some emails, right? You get an email clearly spam, clearly not spam, and you get an email that's like an ad, but it's not really spam. I mean, there's obviously sometimes a gray area that's not clear. Those are not outliers. The outliers, it's a minus in here. So who can deal better with this outlier? A regression or a decision?
Increase the depth in decision.
The decision tree can get it right for the training.
Yeah.
Can isolate that region of the space and get zero training error. But is that good for the testing?
No.
What should we predict if a data point comes in here on the test set?
Plus.
So in that sense, who has a better ability to ignore the outlier that's far away from the line? Is that what you want to say?
Yeah, regression.
Regression being forced to be aligned, even if there's few outliers in there, a few outliers in here, they're gonna contribute a loss, certainly. In the loss function, I'm gonna get a penalty, but it's gonna give penalty for every line. So it's still gonna get them right. So for outliers, typically regression are better than decision trees. And in general, simple classifiers are better than complex classifier. Complex classifier will try to get everything right, and they can because they are complex. But that's not what we want. Getting everything right for outliers means a disaster for the test one.
If there are multiple outliers, won't the outliers move the line of fit
Correct.
towards them and then?
So the outliers, if they're not symmetric, if they're symmetric, there's 3 pluses here and 3 minuses here. Even though they produce a big loss, they don't move the line. But if I have few minuses here and a lot of pluses on this side here, the line will compensate accordingly to the loss function. It's still the square error, minimize the square error, but the square error will push the line a little bit that way, right? And that's maybe not the best line I can have now, because the more outliers I add, the more difficult it is for any classifier to do the job well. Okay, hands up, who's with me so far? Good. What else? Why is bad? I'm going to say this one. There's no restrictions on coefficients. So in other words, the typical regression status is, minimize the loss, this thing here, right? Whatever comes out of it, that's a W. So whatever comes out could be extreme values. Could have huge W's or very small W's or something like that. There is no, in this form, other than give me the minimum of this gradient, it doesn't say anything else. That may not be good. Why would I want the coefficient for a particular feature to not be that big?
Because if you had a test point with a really high value for that feature, it's going to be skewed.
Let's keep the high out of it, what you just said. If I had a test point with a somewhat higher value, right? So the problem with a huge W1 coefficient, I really mean something that's in the billions and the other ones are small values, is that if there is a test point that has, like he said, a little bit this x1, doesn't have to be a huge x1, this is just a little bit bigger x1, that will gonna overwhelm the rest of the summation, right? If this W is really into the billions and the other W's are small values, it means any perturbation on x1 that might happen in some data I haven't seen would cause everybody to be overwhelmed by x1. I'm not saying that's going to happen in the training, maybe it's unlikely to get a billion on the X1, but it's no constraint in here, right? Billion can come out of this equation sometimes. So what people have tried very hard and very efficient to do is to put restrictions on those coefficients.
But if one feature is very powerful and it has a good weight, why it is bad? I mean, maybe.
Right, but how do you know it's powerful? You have a train set, which is a sample of the data. Sometimes it's small, right? Many problems we don't have as much data as we want. Nevertheless, we want to learn from that. Or sometimes the region that's problematic doesn't have enough data. There's enough patients that are easy to predict, but the difficult ones are only few. So you can't really know for sure you have such a powerful feature just because you've seen 3 data points, right? So, I mean, I agree with you in principle. If we know for sure that X1 is the only thing that matters, why not give it the infinity coefficient and be done with it? The other ones don't matter, right? But can we really be sure that X1 is so powerful to assign a billion to it? That means everything will get screwed up. If we are just a little off, this thing is not going to work. So I think it's much more reasonable to say, how about we stay away from billions? And we're still going to give it a high weight, because it looks like it's very correlated with the labels, X1. But just in case stuff happens, we want the other features to still have an impact. Machine learning in that direction, how to restrict the W's to have certain properties, it's a big, big subfield of machine learning. How do we call that?
Adversary.
The process of restricting the W's, putting condition on it. Regularization. So that's a big item. All the regression work in the last 20 years has been on how to regularize regression, but by now we regularize all classifiers, not just regression. So we're not doing what for homework 1 and homework 2, but eventually we're going to hit regularization. We might say we don't want big coefficients, for example. Another property of restriction of W, so one of them is big, no big W. The other one is we only want few W's that are not 0. Sometimes we want this, sometimes we don't. I can't do it right now, all the explanation, but there are cases when we say, look at this thing, we would like to isolate only the features that matter. If I have 100,000 features, maybe cases when I want to use all of them. So I want a lot of coefficients to be non-zero to that feature to contribute to my classifier. But there might be cases when I'm saying, I want only about 1,000 features to matter, so give me the best 1,000 or so, and ignore the other, because there's too many. I think my problem is related to about 1,000 features and no more. And then the condition I put, I say, you still get the linear sum, but I want most of the W's to be 0. So only 1,000 of them out of 100,000 to be non-zero. Yes?
Is there an advantage to doing it that way as opposed to pre-selecting the features?
Yes.
Or like,
So you're saying, can I just do it and pick the biggest 1,000 W's?
or do something like stepwise feature selection, or some other method?
So depends what stepwise means. But definitely it's different than saying, let's do the W normal way, no restrictions, and pick the absolute value highest, 1,000 of them. That's not the same as saying, give me the best line that only has 1,000 non-negative W's. Those are different things. Feature selection, it depends how you do it. I mean, some feature selection algorithms are more complicated algorithms than regression itself. So it's a matter of, how much complexity do you want to add, how much time you spend on it. But what we can do right now, intuitively, why would this be the case? Suppose you are in a domain where you have to explain the result, like medicine. You want to make a prediction and you want to explain it to a doctor. Even though the patients may have many features, the doctors have already a domain knowledge, and it's typically based on not all the features that you have. Right? So if you want to explain something to a judge or a doctor or a lawyer or a carpenter, even though the model that uses all the features might be the one that gives the minimum error, in terms of justification or explanation, you can only explain so many features, right? In many processes, it's not the accuracy that matters, it's the trust that matters. There's subfields of machine learning that deals with whether an image has been forged or not, right? In the court, sometimes they call an expert and say, here's an image that we want to as evidence, but we want to know if this image has been manipulated in Photoshop or not. And the expert comes, does their own thing with algorithms, and then they have to explain, I believe this image has been Photoshopped. Now, who did explain that? To a jury, right? Or a judge. Now, they can't explain that with mathematical algorithms. For the jury to believe it, they have to be a believable explanation. I'm exaggerating the point, but in many cases the justification, in medical domain the same. If an algorithm predicts a diagnosis or a symptom or a problem, for people to pay the money or for people to agree to it, it can't be an explanation like this. Nobody will buy this. Like, maybe you're right, but we don't know what that is, right? But if I say, hey, it's because I've seen this and I've done that, something that the doctor understands, that makes sense, right? There are other reasons for doing this. Both of these things would prevent overfitting in many cases. So without those things, you're much more likely to overfit than you do restrictions. So regularization is a very big deal for regression. We'll get there, and getting there will complicate the stuff because our laws and derivatives will get complicated. Okay, so there are some pluses and minuses here. One thing I want to talk about that will introduce new concept, but we'll talk about informally for now, is I would like to talk more informally than it's written here. Let me see if I can do that. So I would like to introduce the notion of likelihood, but not formal mathematics, just common sense. Likelihood, I have data, like training data, and I have a model. You can call it a prediction model. Like the models you run for homework 1, right? Regression or a tree gives a prediction for the points, right? So a model, let's call it F. F. Say F. It says Y, the label, is approximately f of x, right? That's what the model does. It says I can predict the label y by applying that model f to a data point, and I'll be right sometimes and wrong some other times. The likelihood is, in English, how likely is that data comes from that model. Meaning, if data is generated by a divine power with some algorithm or function, that's not the case, obviously. Data is whatever it's in nature. But if there will be some generation process of the data, is that process actually using f? Right? If that process would use f, my labels would be very accurate, right? Let me write this in a different way. How well data matches the model. Like, since I already have a model and I have the data, I'm not changing the data or the model. That's a done deal right now. I can measure, say, is this data really close to that model? Is the wise I see, how far away are they from the model? So we actually did this already. How did we do it for regression? We said, well, for regression, I erased that picture. We say, here's a point x, right? Here's f of x. Here's y. How did we model that? How good the model matches the label? We say, well, that's the squaring this difference is is how good it matches. This is the difference between f of x minus 1 and squared from a square. Now, I want to do this in a more generative way. So, of course, in the square laws, we say, well, how well the data matches the model? You take a sum over all the data points of f of xi minus yi squared. That's my notion of how well my model matches. How far away the prediction is from the label squared. But in a generative way, so this is called discriminative. In a generative way, I'm going to think like sampling. Again, this is very informal. We don't know what sampling is. We don't know what likelihood is. We don't know anything yet. But here's what I'm going to think. I'm going to think in a generative way, pick a data point at random. What's the chance, probability, that y is f of x? So I pick a data point on x. That could be a patient, that could be an email, that could be an image. I pass it through my model, I get the prediction. And I'm asking, what's the probability that the label is actually that f of x? Probability means if I pick a bunch of them, I pick 100 of them, I'll be right on some and wrong on others, right? So when would this be a good model? When this probability is high, it will be a bad model. The probability is very low. Right? That's how sampling goes, right? If I pick a subset of my data, or if I roll a die a bunch of times, or whatever random experiment, that's called a generative process. And the outcome matches my intuition or my explanation or my prediction. It means my model fits the generative process. If it doesn't, it means my model was wrong, right? So a die, for example. What's my model of a die or assumption of a die? It has, if it's a fair die, uniform probability to see the faces, right? So I start with that model. If I roll a die, I get a certain chance to see each face, 1/6 each. I roll the die 100 times. I count. If those counts end up being roughly equal per each face, I say my model was about right. If I see a lot of 6s and few of the others, my model about the die was incorrect. Right? I'm sure you've seen this kind of story before. So here's I'm going to make an assumption about the generative process. What's the assumption here? In this, when we develop this model with f of x being w sum of wxi, right? What was the assumption? There is a linear correlation between the features and the labels. So the assumption is there is a linearity between features, that's x, and labels, that is y. I'm going to make a different assumption here. So I'm going to forget about the regression for a moment, and I'm going to make the following assumption. The error, which is y minus f of x, let's call that epsilon. The distance there, meaning how far off I am. I could be off high or off low, right? This is off high, this is off low, right? But another data point might be starting from here, this f of x, right? Another data point might be this f of x, but this is the y. That's off high, the other one is what? Off low. So I could get these errors high and low. And my assumption is that the errors are distributed Gaussian. AKA Gaussian is called normal. How many people have seen the Gaussian distribution? Okay, about half. No problem if we haven't seen it. But this is the one thing that if we haven't seen it, we have to get up to speed. If we have seen it and we don't remember, again, we have to recap it. A distribution means I'm looking at the frequencies of epsilon. I say some epsilon here, some epsilon, this is high epsilon, this is low epsilon. So I'm looking at what kind of errors I've seen. And there is a center. Most of them are on average this value. And then the Gaussian distribution is saying, you look at the center, lower errors are unlikely and higher errors are unlikely. Most errors, this is frequency, right? Gaussian means there is a center that's the most counts come in there. If you are close, an error that's close to the center has approximately the same count as the center. But an error that's significantly far off to the center, either side, it's relatively infrequent. And there is a particular form of this shape. Like there's an equation that says the more you go left, the more this shape goes down. Everybody knows that equation? Like right now, you can write it on the board. 1 divided by square root 2 pi. I don't know, I'm looking here. What else? Exponent of x minus the mean, that's this value, square, divide by sigma square, something like that, right? Let's not worry about today. There is a formula that says you start at the mean and that's how you go down, and actually symmetric, left and right. And this distribution is characterized, of course, by where the mean is, and what else characterizes that? Common English, please.
How straight that it is.
How wide this Gaussian is. So one thing that characterizes is the center. The other one, I could have the same center, something very sharp, or I can have something very wide. Right? Variance or standard deviation controls how spread this Gaussian is. Good. We don't want to worry about that formula today, but we'll worry very soon about it. Here's my point. If the epsilon are distributed this way, my likelihood, in a generative sense, I don't want this formula that's mean square error because somebody can accuse me that this comes out of nowhere. Why you take the difference and square them? Right? Maybe I don't want to square the differences. Maybe I want to measure error in a different way. So here's what I'm going to say. Okay, let's assume you have a model and the errors that you get from that model to the label are distributed in a Gaussian fashion. I'm not specifying the mean, the variance. All I'm specifying is that there is a center where most errors go, and as you move far, small errors are unlikely and high errors are unlikely. Here's my likelihood of data. Model. That is the product over all the data points of the probability of seeing that y given that x, so that's y hat and xi, and the model. So W controls the model here, right? My F is sum of W, D, X, right? It's a regression function. So that's the likelihood of data. It turns out we can't work with likelihoods in this way. But first of all, why this makes sense without making, why this makes more sense than the square laws. The square laws, it's something that we come up as a heuristic. Here's the distance, square it, sum it up over the data points. And you believe me because you've seen the square law so many times before, it got imprinted in there. But this is a much more natural notion. It says, this is the probability to be correct for one data point, the data point I. So this is the probability to be correct on xi. And what is this product doing here? And there's some implicit assumption there. Right, this is an IID on data. It says if you want to be correct on the entire data set, it's the probability to be correct on each one of them. That's typically a correct assumption because the data points are selected at random. We assume that the data we've seen, 100 documents, is not a particular 100 documents, it's just random 100 out of how many documents are there. So in most cases, this assumption holds, that if the data was not biased to start with, that would be a huge problem for a machine learning algorithm. If my patients I'm learning from are only one particular kinds of patients, and I don't know that, I'm saying that's all the patients I have, it would be very hard to make predictions in a general case. So we assume the training sets are IID, meaning whatever data we've got there was generated at random from the whole possible set of data. If I can tell you, here's a bunch of images with digits in them. That's what I'm going to do in homework 2. 60,000 images all represent a digit. You guys are going to assume that those 60,000 images are random 60,000 out of all the images with digits that are out there. They're not a particular biased set sample. So this usually holds, IID. The data I have tends to be random out of the whole data that exists of that kind. We don't want to use this, we want to use the log likelihood. That says, take the log of these things. So the log of the product I equal 1 to n of the probability of y given xi and w. It's just easier to work with the log of probabilities for many reasons, including computational reasons. Product of probabilities tends to be very hard to compute. They have so many zeros before you see something that's not zero that computers have these range problems. They can only store so many decimals. Right? So the log of a product is a, so that's a sum from I equal 1 to n of the log probability of yi given xi and w. So I'm going to get to this next time, but my point is, I'm going to replace in here this probability with my model assumption. Let's assume it's Gaussian. And when I replace it, it's going to play very nice because the Gaussian formula has an exponential in it, right? But did you guys say that? So the exponential with the log will cancel out, would make nice, right? So my point would be that if you want to minimize this, should we minimize likelihood or maximize the likelihood? Maximize. We want this probability to be high. We want data to match the model. Maximizing this likelihood will be mathematically equivalent to minimizing the square error. So the point is, the square error is not really coming out of the blue. It has a probabilistic interpretation that says if errors against the model are distributed Gaussian, then minimizing the square error, which is what everybody does, right, actually corresponds to maximizing the natural data likelihood, the probability that data fits that model. Of course, the model is a regression function. We're not going to change that. Maybe the data fits better other models. That's not our concern right now. We're talking about how well it matches a line. So we can, the derivation is in the notes, and we can do this derivation, but I'm not going to insist right now on Gaussian functions. We need the actual Gaussian function to plug in here, take the sum, and show that maximizing that, it essentially comes down to minimizing the sum. I want you to remember the principle, not the actual derivation. That says, this is essentially the same as maximizing likelihood under this assumption. Now, one thing. How strong is this assumption? Somebody can contest me and say, hey, okay, this is not out of the blue, this comes from here, but this assumption of the errors being distributed Gaussian or normal, how we call it, normal distribution, it's as strong as saying the right way to match the data is the square roots. is there a way to counter this argument to say Gaussian is good?
The central limit theorem?
Right. There are many theorems in math that says if you have enough things, you average them hard enough, they tend to be Gaussian. And some other models that show that natural data, not invented by us the humans, natural data, things like how races are distributed, populations, and habitats, and problems with water or whatever, tend to be distributed in a Gaussian fashion. In fact, there's many classes of natural processes. Some distributed Gaussian, some do not. Like waiting times on a bus is not a Gaussian distribution, for example. But in general, Gaussian distribution tends to be the one that fits more likely. There is a center where most things are, and as you move away from the center, things become more unlikely. Now, what doesn't happen Gaussian most of the time is the exact curvature of this belt. The x minus mu squared divided by sigma, that doesn't happen most of the time. But the fact that there is a center and things go down, somehow, that almost always happens. So that's why Gaussians kind of feed the data, because there's aspect of as you move away from the typical center, whatever that is, take the ages of you guys. What's the average age in this classroom? Say 25. 25 is here. There's a lot of 25s and 24s and 26s. And if I move away to 28 or 29, there are not that many, right? And if I move away to 17, 19, there are not that many. So natural distributions tend to have a center and go down somehow. That's why Gaussian fits most of it. So this is not an unnatural assumption. All right, that's what we have. Homework is due next week. It won't be due on Tuesday. Monday is a holiday, so we don't want, homework right after the holiday. It may be on Wednesday or something like this. We'll announce it. But it won't be due after Thursday. So you guys have to work on it. Come to office hours. I don't know if there'll be office hours on Monday because the holiday days have a holiday too. And then we have to move into one more thing. We have to move into if I don't want to do this, if I don't want to do this with matrices, even the exact, is there a different way to get at this? How can I solve this problem without the matrices? Trial and error, right? I try a W, and if it's not good, I try another one. And if it's not good, I try another one. That's very different than solving an exact equation. The question there is how do you try another one that's likely to be better than the one you just tried? Right? So there's some optimization that gives us a different way of solving that. I'm sure you heard about it. So that's what's coming next. So that's another thing. Features almost as an to have a you should stay in the class. Regression can put any question, but that's not but they never take any. They're slightly off. They're minus the inversion is possible, but it would be very hard to take it. I'm turning the camera. That's not happening in data, conditional independence. Okay. But the assumption